With the background of the eigenvalue problem and the process of finding out the characteristic equation, the eigenvalues and eigenvectors, we now proceed to a very crucial concept called diagonalization of a square matrix. Before that, we have to understand the concept of similarity of two matrices. Theoretically, two n by n matrices are said to be similar if there exists an invertible, that is a non-singular matrix P, such that AP is equal to PB. Now, let us see how this should be understood. Suppose we have a matrix A is equal to 1, 2, 3, 4. And if we take some 2 by 2 invertible matrix P, of course, the choices are many, then the matrix similar to A can be defined using AP is equal to PB or B is equal to P inverse AP. Suppose we take P as -8, 3, 5, -2, which you can check is non-singular. Then we can find the matrix B as P inverse AP, and this will give us, of course, you have to work out P inverse for the matrix P. So P inverse into A into P gives us a matrix 8, -1, 22, -3. So this matrix B is similar to the matrix A, but it is not unique because if we select different non-singular matrices P, then we get different similar matrices. Similar matrices have one very important property, that is they have the same characteristic polynomial and hence the same eigenvalues. Of course, you must also include the multiplicities or the repetitions. Two very important definitions have to be understood. One is the algebraic multiplicity of an eigenvalue, and the other is the geometric multiplicity of the eigenvalue. Now let us first talk about algebraic multiplicity. Suppose A is an n by n matrix with eigenvalues lambda. The algebraic multiplicity of a specific lambda is the number of times lambda is repeated as a root of the characteristic polynomial. Now let us talk about geometric multiplicity. Suppose we have an n by n matrix with an eigenvalue lambda. Then you determine the number of eigenvectors corresponding to that lambda. The number of such vectors associated with that lambda is called the geometric multiplicity of that eigenvalue. Now let us understand this a little bit clearly. Suppose we wish to find the algebraic and geometric multiplicities of the eigenvalues of the matrix A is equal to 0, 1, 0, 0, 0, 1, 2, -5, 4. Now, without showing you the characteristic equation, the eigenvalues are computed as 1, 1, 2. Now, corresponding to lambda is equal to 1, if you follow the procedure of finding out the eigenvectors, we get exactly one eigenvector. The distinct eigenvalue lambda is equal to 2 will have the vector 1, 2, 4 as eigenvector. Now, when you build this table with lambda in the first column, the algebraic multiplicity and the geometric multiplicity, we can see that the eigenvalue 1 is repeated twice. Therefore, the algebraic multiplicity is 2. But because it has exactly one eigenvector, its geometric multiplicity is 1. Whereas for the distinct eigenvalue lambda is equal to 2, the algebraic multiplicity is 1 and the geometric multiplicity is also 1. So this concept plays a very important role when we talk about diagonalization. Now let us talk about the principle of diagonalization. The first statement is the key. A square matrix A is diagonalizable if and only if the sum of the algebraic multiplicities is equal to the sum of the geometric multiplicities. The second formal definition can also be understood, but let's go to the third one. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. Next, every symmetric matrix is diagonalizable, but not all square matrices are diagonalizable. So we will now keep all these points in mind. That is the concept of algebraic and geometric multiplicities. Then the conditions for diagonalization, and then what matrices are diagonalizable and what are not diagonalizable. So I present two examples for you. The first example is a square matrix A 1 3 3 minus 3 5 minus 3 3 3 1. Of course, this is not a symmetric matrix, but there is every possibility that non-symmetric matrices cannot be diagonalized. But this is an example where the matrix is diagonalizable. So we find the characteristic equation, lambda cube plus 3 lambda square minus 4 is 0. The lambdas are 1 minus 2 minus 2. And we already know the procedure for finding out the eigenvectors. So corresponding to lambda is equal to 1, we get the eigenvector as 1 minus 1 1. So distinct eigenvalues will definitely have eigenvectors. Now comes the repeated eigenvalue, lambda is equal to minus 2. So when we plug in lambda is equal to minus 2 in A minus lambda into x is equal to 0, we get a homogeneous system of equations. When you find the rank of this coefficient matrix, it returns rank 1, and therefore there are n minus rank number of eigenvectors, that is 3 minus 1, 2 eigenvectors, which you can find as minus 1 1 0 and minus 1 0 1. So let's compile the information in this table. Lambda is equal to 1 repeated only once, so it has got only one vector. So algebraic multiplicity 1, geometric multiplicity 1. Whereas lambda is equal to minus 2 repeated twice, so algebraic multiplicity 2, and we got two eigenvectors, therefore the geometric multiplicity is also 2. The sum of algebraic multiplicities is the same as the sum of geometric multiplicities, so theoretically we can diagonalize. So store all the vectors in the matrix P, and let us check whether the product AP is equal to PA. And we find that both of them are the same. Because AP is equal to PA, this will suggest that A is diagonalizable. And if you want to verify the diagonalization process, just use the rule D is equal to P inverse AP, and you get the diagonal matrix with 1 minus 2 minus 2 on the diagonal, which are incidentally the eigenvalues of the matrix A. So this is how one can diagonalize a matrix provided sum of algebraic multiplicities is equal to sum of geometric multiplicities. Let us now take a problem where diagonalization cannot be performed. So we have a matrix 2 4 3 minus 4 minus 6 minus 3 and 3 3 1. So find the eigenvalues, you get 1 minus 2 minus 2. Corresponding to lambda is equal to 1, we get the eigenvector as 1 minus 1 1 by the normal procedure. And when we take lambda is equal to minus 2 and plug in into A minus lambda into x is equal to 0 and find the rank of the coefficient matrix, we get rank 2. Therefore, the number of eigenvectors will be n minus r, 3 minus 2, which is equal to 1. So only one eigenvector for lambda is equal to minus 2. Because the sum of the algebraic multiplicities is not equal to the sum of the geometric multiplicities, this matrix A cannot be diagonalized. So the key concept of diagonalization has to be understood. Let us keep in mind all symmetric matrices are diagonalizable, but not all square matrices can be diagonalizable. I hope the concept has been understood.